Hi guys, so this problem is kind of more of a concept question where we're just going to work through rearranging some equations and figuring out their relations to each other. So we're going to be dealing with the concepts of spring constants and their relation to frequency. I thought that this would be a good question to go over just so that you guys can kind of get an idea of their relations for later use. So here we go. In this specific problem, they're asking us about a frictionless table where there's two springs and they're kind of connected and they both have their own spring constants. And then we're going to try to find that the block's oscillation frequency in terms of frequency F1 and F2. So how it would oscillate if it was attached to spring 1 or spring 2 alone. So the first thing we're going to do is kind of think about this situation given by the problem conceptually and identify the forces that are at play. So an important equation to know for this problem is that the expression for spring constant of a spring is K equals F divided by X, where F is the force being applied on the spring and then X is the displacement of the spring. So that means that F1W and FW1 are the forces exerted by the spring 1 on the wall and then the wall on spring 1. And then spring 2 is in contact with the mass, so that means that the net force on the mass is Fm equals F2m, so the force of spring 2 on the mass. So now that we've identified the forces at play, we can kind of rearrange the equations and calculate spring constant. So you'll see that we start with just the regular equations for each force that's at play, and then we end up finding the net displacement of the mass. Again, I know it's confusing because there aren't really any numbers in this scenario, but this means that you can apply these concepts to any equation, any scenario in which they do give you numbers. So this is kind of how you find the net displacement of the mass, just substituting in different values that are equal, and then you find the net force on the mass. And then from those two equations, you can put them together so that you can find the total effective spring constant. And then we can kind of relate everything that we know to calculate an angular velocity. So you'll see we just start with that normal angular velocity equation, and then we substitute everything that we know that we found in the previous steps. Then we use that to calculate the frequencies of the oscillations, and we're going to do it for both spring 1 and spring 2. So those are going to be two separate equations. But then we know that the actual frequency is just a multiple of the angular frequency, and we have the equation for that. So we plug in what we know, and then we find that F1 and F2 are the frequencies of oscillations of spring 1 and 2, and you can see their relation in that last equation there. So hopefully from this you can see that all of these equations are very linked, and if you have certain variables, you can definitely find the others. So hopefully these equations are really helpful and you can see how the math was done. If you have any questions, email me, schedule a session. Again, hope this is helpful.